Okay, well, we'll get started back up now. And so what we just saw was an example where there are the five top models give us different impressions about what might be important. They all agree on certain things, but there's some disagreement because they're different models. There's some uncertainty as to the importance of some of the other variables. And a natural question is to ask, how much uncertainty is there? Is it meaningful uncertainty or is it not? And this is one of the problems with the classic approach that has been taken when one typically applies something like all subsets regression, is that choosing a single best model fails to acknowledge the uncertainty involved in that process. As statisticians, we always like people to show us standard errors, but what's the standard error on the model selection process? We don't put one on there. We just grab the best model and run as if we'd known that all along. But the problem is that we estimate parameters of the chosen model as if it were the only one we'd considered. And in particular, any parameters, any variables that we exclude from the model have parameters that are automatically estimated to be zero with zero standard error. And somehow that doesn't make sense in a lot of cases if you're not really sure that a certain variable should be included or excluded. If it's excluded, you're assuming that the standard error is zero, that you knew that it belonged out. And that kind of bothers a lot of people, as well it should. And in fact, often there are many, many models with very similar information criteria values. Information criteria are statistics. If I were to take a new sample of data, I wouldn't get the same values of those information criteria. They're subject to the random errors in my data. And so different models will be ranked higher or lower in different samples from the same population. So to pick one of them and pretend there is no sampling variability in it is a rather callous thing to do, really. So, in fact, we saw that, and this is expressed here by saying with a small change to one or two observations, a different model could have been selected. It's easy to imagine that could have happened. And we saw that in the place-kicking example where this phrase here, 12 models within 2 information criterion units, it turns out that 2 units of information is not very much. So when we see all of these models here, within 1 unit of information of one another, they're not really all that different with respect to how much the data support them. So models near the top tend to have some variables in common. Can we use this somehow? So instead of selecting one model, we can use all of them to evaluate the relative importance of all the variables. That is, we can transform, and I won't get into the details of how this is done, but we can transform the information criterion into another quantity called an evidence weight. And we do that using something called the softmax transformation. I won't worry about the softmax transformation. If you know about it, that's great. If you don't, it's not important. The point is that we can create these evidence weights through some transformation of the information criterion. And these evidence weights have some properties that make them sort of look and behave kind of like probabilities. That is, the evidence weights across all the models will sum to 1. And the higher the evidence weight, the more evidence there is for that model in the data. And in fact, if BIC is used, if you decide you want to use BIC, then they can be shown to be approximately posterior probabilities that a model is correct given the data. If you wish to follow a Bayesian paradigm and put certain priors on things, put equal priors on all the models and normal priors on the parameters of those models, then you can show that these actually do behave like probabilities, like posterior probabilities that the model is correct. So in any case, whether you're using BIC or something else, a value close to 1 means that the data strongly support that model. And values close to 0 mean that the data don't have real strong support for that model. Once we've calculated evidence weights for every model, we can calculate evidence weights for each variable simply by taking the sum of all of the evidence weights across all the models in which that variable appears. So for example, for distance, Distance appears in all the best models, so we'll add all the highest evidence weights together, and the result will be something close to 1. Whereas one of those 3 variables that was useless appears in none of the top models, and we'll add only kind of middling and low variance weights evidence weights together, and the result will be something closer to 0. This process is called model averaging, and if you use BIC, it's called Bayesian model averaging. So variables that are often in the top models have evidence weight near 1, and variables that are never in the top model have evidence weight near 0. So let's go back to the top 5 models, and now we can interpret what these things here were. These are the evidence weights for the models. Notice that the best model has evidence weight only 0.067. This is not a model that the data are saying, yeah, I like that. This model bubbled to the top by chance. There's a lot of uncertainty involved in selecting a best model here. There is not one model in this data set that is being strongly supported. All of the models have just a little bit of support, but there will be trends in the models. As we said, all of the best models involve distance. All of the best models involve PAT. And so we'll be able to suck that information out of the models by taking all of the models and adding together the weights for the models that have distance in. Because later on, when you get down below here, there are weights that look like this. Something, something, something. Those models are effectively useless. So we can pick out the variable weights by looking at the coef on the model object from GL-Multi. And I've created a new object called parms, and that's just pulling out the coefficients. And now I've added some extra column names here to help us interpret the results. And I've printed the results by rounding all of the numbers to 3 digits. Otherwise, these are ridiculous numbers of digits. And I would have done one more thing had I thought in advance to do that. I would have flipped this entire list around because it's listed from worst to best. I'd like the best to be at the top. So instead, we have to read at the bottom, the evidence weight for distance is 1. That means there is no ambiguity at all about the importance of distance in the model. The evidence weight, ignore intercept, that's always going to be in the model. The evidence weight for PAT is 0.992. Well, there's very, very strong evidence to say that PAT belongs in the model. These guys here didn't have very high evidence weights, and they're only as high as they are because there are so few models that we considered anyway. And then we said we had these 3 variables here that were somewhere in the middle, and we see that they are indeed kind of somewhere in the middle. It's not totally clear that they belong, but it's not totally clear that they don't belong. You could use a rough cutoff of 0.5, or you can interpret them more qualitatively and say, well, you know, they kind of seem somewhat important, but not terribly important. So now we've actually got sort of a ranking on the importance of the variables, rather than just this model is good and the rest are bad. Much, much nicer. You want something practical. This is very practical. Other than the fact that people don't understand it when I do it, I like taking the results to them and showing them the results because they like the results of this a lot. Well, you know, that whole notion of model averaging in all subsets is fine when you don't have too many variables, but sometimes the number of variables is just so large that there's no way you can even approach doing something like that. So what you need to do is find some way to efficiently filter out the bad models, filter out the bad variables, and identify good ones. So there are a number of ways to do that. You can use something called a genetic search algorithm, which is built into GL-Multi, and that's something that's compatible with model averaging. You can do what in the past we thought of as the classic approach to model selection, to variable selection. You could do a stepwise procedure, or you could do something a little bit more modern. I think. What did Hasty call it in his talk yesterday? I forget. He called it something like middle-aged. It's no longer. A millennial, that's what he called it. It's a millennial approach. It was developed in the 1990s. So is that new? I don't know, but not everybody's using it yet. So it's still kind of new to a lot of people, the Lasso. So the genetic algorithm is basically a way to explore a model space without investigating every model. So here's the way you can think about all possible models. Suppose you have 100 variables. Create a vector 100 units long. And in each slot of the vector, there's either a 0 or a 1. It's a 1 if that variable is in the model, and it's a 0 if that variable is not in the model. So the best model is going to have a few 1s in there and probably mostly 0s. You never know, but that's what you might expect. And the locations of those 1s in the best model will tell you which variables are the important ones. So what you're trying to do is sift through all possible 100-length binary vectors to try to find the best one or the best combinations of them. It turns out that a genetic algorithm is really good at doing that. It does exactly that very well. And without getting into the whole details of it, it has an aspect of randomness to it that allows it to jump around and explore different sets it basically selects certain combinations of variables, so it selects certain vectors, and then it tends to explore in an area around those that have some similarities to those. And sometimes it can jump to a new area and look around there, and jump to a new area and look around there. It's a smart algorithm that ends up focusing on models that have good information criteria values. It's called genetic because it basically takes models that have high fitness, that have good information, and it allows them to stay around and create variations of them. And it takes models that have low fitness and it just says, you're no good, I'm getting rid of it. And in the end, you finish with a set of, say, 100 models that are the best that you ever created and tried out of that list. There's no guarantee that you'll find the one very best model. So if you're seeking the one very best model, well, first of all, I've just told you shouldn't do that. And second, there's no promise the GA will find it for you. But what it will do is it will tend to pick out sampling among the best models fairly well. And if the same variables are in the top models, then they'll have a very strong evidence weight regardless of whether you've managed to hit every one of those top models. So it's very good to be used in conjunction with model averaging. It's good at finding the good models or the good variables out of the pack. That is available in GL Multi. Instead of using method equals H, you can use method equals G. Stepwise procedures you're probably already familiar with. They build models one variable at a time. So you can do forward stepwise, which starts with nothing in the model, and then it adds the best variable, and then it figures out, given that variable, what's the best next variable to add, and given those variables, what's the next best variable to add, and so on. And so it builds models in a stepwise sequence. You can do backward elimination if you can fit the full model in the first place, and get rid of variables one variable at a time, each time getting rid of the worst variable. And then you end up selecting the one model that has, say, the lowest information criterion. Notice I don't recommend doing things like hypothesis tests or using significance levels to make your selections or to do your stopping. If you want to do that, that's in our program Stepwise Place Kick, but I just don't especially recommend that. That's not generally a great thing to do unless you are just sold on picking one model out of all subsets and you want a fast way to do that. It doesn't necessarily find the best model from all subsets anyway. And then there's the Lasso, and the Lasso stands for Least Absolute Selection and Shrinkage Operator. And if I've learned many things from reading Tibshirani's work, hasty Tibshirani Friedman's work, but if there's one thing I've learned is that if you invent something, you have to give it a name people can pronounce. And so we have the Lasso. The Lasso is kind of like an information criterion approach, except it's different. Instead of fitting the model and then adding a penalty to the log likelihood, the penalty is actually in the fitting process. So it penalizes you for having the variables expand in size. That's what this says. You end up trying to maximize this quantity here, where this is the normal log likelihood, and then here is a penalty, which says as the magnitudes of the parameters grow, I'm going to cut down against this log likelihood that you're trying to improve. So if your parameters If your parameter estimates get very large without really helping this, then you're going to lose a lot in your penalty and not have a good model anymore. So it ends up, because of some magic of using, in particular, the absolute value here, it ends up shrinking some parameters towards 0 and setting the rest of them to exactly 0. It often performs better at prediction than stepwise, but it does tend to retain some variables with uselessly tiny coefficients. And it's actually not very good at estimating parameters for variables that are clearly important. It ends up shrinking those parameter estimates down inappropriately. And also, there are no inference procedures around them, or at least not very good ones that are well established. So there are ways to do hypothesis tests, and they're developing ways to do confidence intervals, but they're not well established and not well studied. Yes?
I think also ridge regression is another technique.
Ridge regression puts a square there. Does exactly the same thing, but it doesn't do variable selection. All it does is shrink the variables. It doesn't set them to 0. That's the magic of the absolute value, is that it causes, because of the shape of this constraint in P space, it causes variables to get knocked down. It causes parameters to get knocked down all the way to 0 quite easily. Ridge regression won't do that. So you'll shrink your parameters, but you'll still have as many as you had before. So I have a program for that. We have a program for that called Lasso Place Kick, where you can see how it's applied. I don't have time to show you all of these things and still tell you about them, but hopefully you'll have a chance to download those from the website and play with them on your own.
So in the case of Lasso,
Mm-hmm.
the AIC, BIC, CAIC, they are not relevant.
They're not relevant, no, that's right. You've already pulled the penalty notion into the log likelihood. And in fact, anybody happen to go to Hasty's big talk yesterday? So one of the things that Hasty recommended is, and I'll write this down here, there is something called the relaxed lasso, which you can look up. It basically takes the lasso and says, okay, thank you for selecting variables for me. Now I don't like your estimates anymore. I'm going to go back and use, in the case of linear regression, I'm going to go back and use the least squares estimates, and then I'm going to put a separate parameter on them to decide how much I want to move between the least squares estimates and the lasso estimates. So it lets you pick something between the least squares and the lasso. I don't recall whether it is fully applicable theoretically and implemented for GLMs. I suspect that it is, so that you could probably use a relaxed lasso in GLMs. Hasty's simulations yesterday were specifically in the context of linear models, but over a somewhat broad series of circumstances, he found that the relaxed lasso was much better than the regular lasso, all subsets, or stepwise for estimating parameters and doing prediction. So I might actually suggest that if you're interested, look up relaxed lasso. If I remember right, I'm operating totally on memory here. There might be a function or package called relaxo that will do the relaxed lasso. So once you've found your model, you might want to know whether you are any good at whether the assumptions that you've made all along are any good anyway. That is, just like in a linear regression, we assume things like a straight line and equal variance and all that kind of thing, and any of those assumptions could be wrong at any given time. Well, in each of these models, we're making assumptions, and any of those assumptions could be wrong. In linear regression, we use residuals to identify model assumptions that might be inappropriate for the data. And the residuals are just the observed value minus the predicted value. And we use them in things like plots. We use them in plots to identify a poor mean fit. For example, there might be curvature where we're assuming a straight line. We use them to identify non-constant variance because the usual regression model assumes that the variance is constant everywhere. And we can use them to identify outliers and influential observations. So, you may see a residual plot. The typical residual plot is supposed to look like just a cloud of points. and then you have a point down here, and you might identify that as being like an outlier, where this is the residual, and this might be x or it might be y hat. We can use residuals, and there's a standardized version of residuals where you can divide the residual by the variance of the residual, and that's often used, in particular, it can be helpful for outlier detection. So we can use residuals similarly for all of our count models, but there are a couple of challenges that make them a little bit more complicated than residuals in linear models. First, we need to define the residuals in the context of each model. And second, we need to identify the assumptions that we're trying to check, because these models have different assumptions. For example, variance assumptions are not present in these models in the same way that they're present in the linear models. So to start off with, we'll look at how to actually compute residuals for count data models. And the first part of the process is you have to express all of your responses as counts. Now, in the case of a Poisson regression, you're already observing counts as your responses, so it's already done. There's nothing new to do. If you've done a Poisson rate regression, then you need to multiply your rates by your exposures to turn them into mean counts. The tricky part comes in a logistic regression. And here's the problem. For example, in the place kick data, we observed individual place kicks that were either good or not good. They were zeros or they were ones. Think about a model where you put a pi hat next to that. So you've predicted the probability of success, and now you want to make a residual. Your residual is either going to be 1 minus pi hat or 0 minus pi hat. There are only two possible values for the residual. They're not very useful residuals. You can't look for outliers. There are two possible values. What's going to be outlying? You can't look for problems with the model, because at every point of x or at every point of pi hat, there are two possible residuals. They're completely useless when you have purely binary data. So you have to make your data into aggregated form, and Chris showed this earlier when he said, let's aggregate the data by distance and find all the 20-yard place kicks, all the 21-yard place kicks, all the 22-yard place kicks. And then he had a number of trials and a number of successes. That's what you have to do here, except that you have to do it for all counts with the same combination of explanatory variables that are used in the model. So if you have one variable in the model, for each value of that variable, accumulate all of the trials into one count of successes and one count of total. If you have two variables in the model, take every combination of those two variables and accumulate all of the trials and successes. If you have 10 variables in the model, you might not be doing a lot of accumulation, because every combination of those 10 variables might be unique. If that's the case, then using residuals is not going to help you. Using residuals will only help if there is indeed some accumulation that you can do so that your numbers of trials aren't all 1. So now you have, say, m different, we call these explanatory variable patterns, and to call that data explanatory variable pattern form, or EVP form. You now have capital M different explanatory variable patterns, or M is just the total sample size in Poisson count models because you didn't have to accumulate anything. And you have an observed successes, an observed predicted value, and in the case of a binomial, a number of trials for each of those M's. So you can calculate the standardized Pearson residuals. The standardized Pearson residual is basically just the residual in the numerator, exactly the way you would compute it in a linear regression, divided by the square root of the variance of the random variable, or of that quantity, ym minus ym hat. There is a formula for that. It will vary depending upon the model that you fit. That's why I'm not showing the formula. It has a different function down there depending upon the model that you fit. But it all boils down to the same thing. And the residuals are available for you quite easily from a function in R. So you don't need to worry about the exact formula for that, but you can look it up in the book if you'd like to. The nice thing about these quantities here is that they're approximately, I'll put a square around that because that's important, approximately standard normal when the model is correct. And particularly true as long as the predicted values are somewhat large, which means they're around 5 or more. And in the case of a binomial, that also the predicted number of failures, in addition to the predicted number of successes, are also at least 5 or more. And in that case, if they start acting like their standard normal, then one of the things you know is that from the standard normal distribution, about 5% of the population ought to be beyond plus or minus 2. You hardly ever should get anything beyond plus or minus 3, and it'll be a cold day before you get anything beyond plus or minus 4. Unstandardized versions of these residuals also exist. The standardized ones are better than for diagnostics, and you can also create a version of the residuals based on contributions to the deviance. We don't worry about them that much because we generally prefer the standardized Pearson residuals for doing diagnostics. So the first diagnostic I would do with any residuals is I would make residual plots. So I would basically plot the residual R against some quantity out here, and that quantity could be, for example, it could be y hat in the Poisson or pi hat in the binomial, or it could be x if you want to look at how the residuals change across a particular explanatory variable. And what will happen is, just like in linear regression, if the model fits, this shouldn't show any serious fluctuations in the mean value. So I'll draw a bunch of things like this. So you shouldn't see obvious curvature like that. You shouldn't see, well, any other thing that would suggest that the mean is not constant. It should be a mean that varies around 0. So you hope for something that just scatters all around 0. Furthermore, it should be roughly constant variance, and you shouldn't see too many points beyond. You can draw lines here at 2 and minus 2. You can draw a line up there at 3 and minus 3. You should be able to gauge how many points there are beyond those thresholds and have an idea of whether or not there are few or many points beyond there. Curvature in this plot suggests that either the log or logit specification curvature if you plot against y hat, curvature in this plot suggests that you've used the wrong link, that the log or the logit should have been something else. What? Well, I'm not sure. So maybe plotting the residuals against the linear predictor might be able to help diagnose how it needs to be changed. If you see the curvature more clearly there, maybe it suggests some other function that you need to use. Although, quite honestly, I've never come into a problem where I've been able to look at any plots and say, I know exactly now how I should change that function. But in particular, if you're working with somebody who might have a suggestion of things that are used in their discipline, you might try other things. Changing variance shouldn't happen because the residuals have already accounted for possible changes in variability in the responses. Remember, the variance changes with the mean in the Poisson, but the residual has already accounted for that. So it should have evened all of that out. So if you see anything that looks like that, that's a problem. That means you've chosen the wrong model somehow. That the variance portion of the model is not what your data are expressing. Your model has not adequately fit the data. And if you see points beyond the thresholds, well, 1 or 2 past, say, plus or minus 3, they might be outliers. But if you have a lot of points beyond plus or minus 2 and some beyond plus or minus 3 and plus or minus 4, that's a sign of a different problem called over-dispersion. You can make the same plots against each explanatory variable, and the only difference is that if you find curvature in those plots, it's suggesting that a transformation or polynomial terms are needed for that variable. But if a lot of them have curvature, then maybe it goes back to the link function, that the logit or the log was the wrong thing to do, because it's messing up all of those plots instead of just one of them or maybe two of them out of a larger number. And then the warning. Once again, I point out to you that in a binomial with only one trial, there are only two possible values of the residuals, and that's not very useful. Your residual plot always looks like this. That's what every single residual plot looks like from binary data. You can't learn anything when you already know what it will look like before you run the analysis. So you just don't use residuals when you have binary data. In a Poisson, when y hat is very small, I mean like well below 1 especially, if your mean count is 0.1, then that means that most of the time you're observing a 0. Sometimes you're observing a 1, and you'll hardly ever observe a 2 or more. So you're back at almost the binary problem, and you have the same problem. You just have bands in your plot. In binomial models, furthermore, extreme residuals can occur quite normally between near pi equals 0 or pi equals 1. It just happens. And it's because the correction doesn't account for the fact that near pi equals 0 and pi equals 1, we don't have an expected count greater than 5. We have very small expected counts. You know, if you have a probability of 0.99 on 3 trials, your expected successes and failures are not both going to be very high. So your residuals don't really follow approximately a standard normal there. And using those 2, 3, 4 cutoffs is just not appropriate. So don't take these things too literally, especially in small samples. Don't take them too literally when you have small expected counts or when you have small numbers of trials or small numbers of different possible values that you can take on. However, if you have larger numbers, then you can start to take these things much more seriously. So if you have larger numbers of trials and you have expected counts, predicted values that are more moderate and large, then you can start to believe them. So let's take a look at some diagnostics on the place kick data. And I'm going to reduce this model down to distance only for a very specific reason. I'll get to that reason later. But one of the reasons is that it's easy to do. I can show you this very easily. So the first thing I need to do is I need to aggregate the data. Right now I have individual place kicks, and I need to aggregate this, and Chris has already showed this aggregation before. So now I have one observation of 3 trials and 2 successes at 18, 1 at 19 with 7 trials and 7 successes, and so on for every different distance. So that's what I've done first. I've aggregated the data. Next, I'm going to fit the model to the aggregated data, and the formula now that I have aggregated data, I have a variable called success, which counts my successes, and a variable called trials, which counts my trials, and I still have distance. So in my model, my formula, instead of saying good here, which is how we modeled the binaries before, instead, I'm saying successes divided by trials in the left-hand side of the formula. And I will say that as a function of distance. And then we have weights equals trials. Chris already showed you this. The nice thing about it is that it gives back exactly the same parameter estimates and standard errors as we got before. We're not changing the model fit. We're just changing the information around which the model is fit. We're changing the way the data are presented to the model fit. We're not changing anything about the fit. So now I'm going to add the predicted values by running predict. I'll call them pi hat. I'm going to add the regular residuals for no reason other than just to show you that they can be done, but I'm rather going to prefer to add the standardized residuals using the R standard function, saying type equals Pearson. I could have said type equals deviance. I'm adding in the linear predictor by pulling the linear predictor element out of the mod fit bin object. And I'm dumping all this stuff into a data frame. So now here's my original data parts, and there are my predicted values, my Pearson residuals, my standardized residuals, and my linear predictor. And that's a column that I'm especially going to be interested in. And already, if you look at that, you start to think there are problems. Just in the first 6 observations, we have 2 of them above 3, which shouldn't have been happening. And we have 1 above 2, which already starts to make us suspicious. So let's take a look at plots. We've added a low S curve. This is a program we have that will allow you to automatically make these plots out of your model fit. What I want you to do right now is, on your paper, take your thumb and cover up that point. Look at the rest of the points and ignore the red line squiggling through it. What do you see? What's that? A possible trend? A positive trend, yes. Exactly. Kind of looks like it does that, doesn't it? Remember, they're supposed to form a scatter, but they don't. It looks like there's a positive trend. We have points that are above plus or minus 3. We have what appears to be a positive trend. We have several points that are above 2, and a lot of those points are happening down here at the low end. Something funky is going on with the fit at the low end of this function. Having this shoot way, way up, here, 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 going way up like that, that is weird. Most of the time, I would expect this just to sort of bounce around kind of flat like that. So something odd is happening, and especially something really weird is going on with that point. Why is it pulling the line up like that? Well, okay, we have these 2 extreme residuals beyond plus or minus 3. But the extreme negative one is just an artifact of the discreteness near point 1. In that particular one, we only have 3 trials, 2 of which were successful. The probability, Chris already pointed this observation out to you, the probability of success was 0.977. So if you give yourself 3 kicks, and there's a 97% chance of success on each of those kicks, you really do expect to make all 3. And a fluke happened and you missed one. Okay, so let's go back and be binomial about that. What's the chance that you miss 1 kick in 3 when the probability is 0.977? The answer turns out to be 6.7%. There's a 6.7% chance of missing 1 kick out of 3. It doesn't happen very often, but it's not as rare as 3.5 is on a normal. That's an example of the normal distribution not fitting a small number of trials with a high probability of success. The real probability is 0.067, but it's giving you a probability estimate that's like 0.000 something. So that's an artifact. That's a fake thing that's been thrown to you because of the smallness of the data in that area. On the other hand, the extreme positive value isn't a problem because there are 789 kicks with probability 0.971. There are plenty of observed or expected successes and expected failures there. And the model is clearly underestimating that value. 6 residuals have magnitudes of 2 or more. 1, 2, 3, 4, 5, 6 residuals have magnitudes of 2 or more. 4 of them happen right down here in this low region. That's a little bit more than the 5% we'd expect to see out of 43 observations. So something is happening that's weird with the logistic model at low distances. Furthermore, as I pointed out, ignoring that one big positive value, it looks like there's a sloping trend, and that just shouldn't happen. This plot is screaming at us that there's something wrong with this model. Something is weird about that extreme positive residual. Well, let's stop and look at the data for a minute. You want to be practical, let's look at the actual numbers that made that up. What is happening there? That one distance is 20 yards. And Chris already quizzed you. What's unique about 20 yards? That's where an awful lot of the kicks are from points after touchdown rather than field goals. And what did I say about points after touchdown? They occur in the middle. So what happens is the model is underestimating the probability of success. It doesn't realize that a lot of those kicks are points after touchdown that have kind of a higher probability of success than the rest. Furthermore, defenses don't really push very hard to stop points after touchdown the way they do to stop field goals. So they have a higher probability of success than merely the fact of their being at 20 yards suggests they should. So what this is telling us is that we need the PAT variable in the model to distinguish between those kicks and the rest of the kicks at 20 yards. Do you remember what variable selection told us? We needed the PAT variable. So what we've just done is, through diagnostics, discovered that we're missing a variable in our model that we already knew we needed. So if you use diagnostics well, if you use the residuals carefully and you learn to interpret them, they can tell you a lot. But you have to be careful in interpreting them. Any questions about that? Now you see why I reduced it down to a model we knew wasn't right, so that we could go back and turn up the model that we thought would be better. The problem with residuals is all that stuff that I showed you, if it was your first time looking at a residual plot, you would probably never have found. It takes experience looking at residual plots to start figuring out how they work.
Is this technique of covering one of these values something that we use a lot?
It is, yeah. Because sometimes the mind is drawn to odd things in the plot. And when there's an odd thing in the plot, it can mask an awful lot else going on. I do that a lot.
Did you notice that on the second plot there's a negative slope?
Yeah, that's because the two plots are basically just inverses of each other. The second plot is against distance, and as distance gets large, probability gets small. So the two plots are basically just, they're not exactly, but they're essentially inverses of each other.
What if there's sort of explanatory variables which are not continuous?
Yeah, some of our explanatory variables in this were binary. For example, PAT is binary.
But if I'm just thinking about the online retailers, they're trying to use the Poisson model to predict how many people are purchasing for each time, each hour. So it's like a 24/7 for one week. Then the explanatory variable is sort of it's in a way some dummy variable or categorical variables as opposed to these variables. If that's the case, then do we expect the residual plot to be similar to that?
With categorical variables, you probably would do something like list the residuals at each value, but residuals act differently with categorical variables than with numerical variables. For example, it's easier to see in a linear model. If you have a variable in the model, then the differences around the mean are going to average to 0 for both of them. So the only thing you'd be able to see is a change in the variance. You wouldn't be able to see a change in the mean because there wouldn't be a slope. It's only if you left the variable out of the model that you might see a slope to the residuals. So the problem with those residuals is that it takes experience to learn to do them, to learn to use them. And I think Will Rogers once said that good judgment comes from experience, and a lot of that comes from bad judgment. So, you know, trial and error is the way to go about figuring out how these things work, but you never know if you don't get the feedback to know if you were right. So people like to have objective measures, quote-unquote objective measures of the fit, where they don't have to look at stuff and try to interpret it. They just like to have a number handed to them that tells them this is good and this is bad. So there are goodness of fit statistics that are numerical summaries of the model fit. So you don't have to just sort of look at them and try to figure out what's happening. They're less touchy-feely. They're more objective. And they try to summarize, the problem with them is that they're omnibus measures, and they try to summarize many aspects of the fit into one number. And if you ask one number to do 20 jobs, how well will it do any one of them? So they provide little information regarding the cause of any poor fit that they detect. They just might tell you that they don't like something about the model. Goodness of fit statistics are kind of what I call Mr. Jones statistics, because I always imagine Bob Dylan singing, "You know something is happening, but you don't know what it is." And that's all they do. They tell you something's happening, but they don't tell you what it is. And it leaves you to go and try to figure out what the problem is. So that's why when you do use goodness of fit statistics, you should use them in combination with residual plots. Don't use them in absence of residual plots. They can sometimes help to confirm what each other is seeing. Sometimes they tell you contradictory stories. One of them might tell you something's wrong. The other one might tell you, no, there doesn't look like much. Well, then you've got to do a little bit more digging to figure out what the story really is. The goodness of fit statistic may not show problems if a model mostly fits well, but there's a problem that you might detect in a plot. But it's like I said, it's trying to do 20 jobs at once. If there's one problem with the model, it may not detect that. The most used goodness of fit statistic is the residual deviance. The residual deviance compares the predicted counts from the model against the observed counts using the log likelihood. So I already explained that a saturated model gives you back a residual deviance of 0. The model fits perfectly. A smaller value of D means that the model fits the data more closely. That might be a good thing or it might be a bad thing. When your model fit the data more closely, maybe you've got so many parameters in your model that it's just zigzagging randomly around, touching all the points. That's not always a good thing. The residual degrees of freedom are equal to the number of explanatory variable patterns minus the number of parameters in the model, p variables plus 1 intercept. The number of fitted points minus the number of parameters. And the first thing that people will do with this is that they'll compute the deviance divided by the degrees of freedom, deviance over degrees of freedom. And if the model is correct, we expect the deviance over degrees of freedom to be somewhere in the neighborhood of 1. Because in theory, the residual deviance should behave sort of like a chi-squared random variable with this number of degrees of freedom, and that's the expected value of the chi-square, so you expect the number to be somewhere close to 1. And large values indicate a poor fit. Of course, you'll find nowhere in the world where it's published that says what large means. So that becomes somewhat difficult for a person to interpret. Is 1.5 large? Is 3 large? Is 100 large? What's large? We have an extremely, extremely rough guideline that you can use, but I don't really recommend that you take it too seriously. It just gives you an idea of whether something is possibly a large deviance over degrees of freedom ratio. And it's based on the normal approximation to the chi-squared. So if you have a large enough number of degrees of freedom, if this isn't too small, and I really can't tell you what too small means, then you can compare your deviance over degrees of freedom to these quantities here, where if you're within 2 times the square root of 2 over df. That indicates a potential problem, and if you're beyond 3 of those past 1, then that's clearly a bad fit. But the statistic, once again, tells you nothing about the cause of the problem. It just says, hey, it looks like something's wrong here. And furthermore, here's the big problem with it. It doesn't work great with continuous explanatory variables. It works much better if all your explanatory variables are categorical. It doesn't work well with continuous explanatory variables. If you don't like the likelihood ratio statistic, you can compute the Pearson statistic, and it does the same thing. And the degrees of freedom are the same as for the deviance, and so you can compute the Pearson over degrees of freedom instead of the deviance over degrees of freedom. That's not normally done. Usually it's just the deviance over degrees of freedom. So in the place-kicking example, the residual deviance and degrees of freedom are printed in the summary for the model fit. So we're extracting the necessary components for the calculations and printing them out separately. So I can get the residual deviance from the mod fit bin, the deviance element of the model. I can get the degrees of freedom from the df residual element of the model. I can make my ratio there, and I can compute my 2 thresholds, the 2 version and the 3 version of the thresholds, and I can print them all out. So this is my deviance, this is my degrees of freedom, this is my ratio. So that's the statistic I'm looking at, and these are my 2 thresholds. So even though we have already determined that this model has a big problem with it, it's missing a variable, the deviance over degrees of freedom didn't find that. Now, as I've said, I'm not a huge fan of this statistic, but it's used a lot. Why am I telling you about it? It's used a lot. You're going to run into it. You're going to be asked to produce it. You're going to have the opportunity to read about it, and now you know that it can be taken with a grain of salt most of the time. So this says there doesn't seem to be any serious problem with the model fit despite our interpretation of the Pearson residuals. So that suggests to me that maybe the model mostly fits, with the exception of the problem that we've left out the PAT. But the model isn't an abysmal fit all the rest of the way. There are formal goodness of fit tests. In the binomial model, there's something called the Hosmer-Lemeshow test that is like the thing everybody learns about. The Hosmer-Lemeshow test it's even better than the goodness of fit statistic because it doesn't just give you a number you can't interpret, it gives you a p-value. And if I have a p-value, I can do anything. The p-value is as good as the statistic it's based on. So the Hosmer-Lemeshow test mainly looks for problems with the mean or probability portion of the model. It's not looking for problems with over-dispersion. It's not looking for problems with omitted explanatory variables. It's not looking for problems with having for choosing the wrong variance part of the model. It's only looking for problems where the mean doesn't seem to go where the curve suggests it is. We have a function that will compute that, the HL test function, and it's available in the script that we've got online, the allgoftests.r. That script also does other goodness of fit tests that we describe in the book. That's available for the binomial model, the logistic regression model. You can do a similar thing for Poisson models. Although that test is less well known and less studied, we have a function that will perform something very similar to the Hosmer-Lemeshow test for Poisson models, so you can get a p-value out of that too. But we don't know how well it works, really. And in fact, right now I have, this guy's amazing, I have a second-year undergraduate. Summer of his sophomore year is doing a research internship with me, and he's cracking apart both the Hosmer-Lemeshow and post-fit goodness of fit tests and finding problems with both of them and figuring out how to correct them. This guy's like way smarter than I even wish I ever was. He's amazing. So hopefully someday, maybe in the next edition of our book, we can write about an improved version of both of these tests. It'll be called the Suryanovich-Logan test.
Stan Logan, it's easy.
No, Suryanovich. It has to be his whole name. So finally, we'll get to this notion called overdispersion. I've mentioned it a few times. What is overdispersion? Overdispersion is a little bit of a foreign thing if you're used to linear regression modeling, because the normal distribution has this flexible thing called variance. It has a separate variance parameter so that you can have any combination of mean and variance you want. Whereas, as we've pointed out, in the binomial distribution, the variance is tied to the probability and the number of trials, and in the Poisson distribution, the variance is tied to the mean. That's an assumption. That's something that the model says that it's going to pretend is true. I like to use the word pretend instead of assume. So those are model assumptions made for mathematical convenience. They don't have to be true in reality. And in fact, often counts or proportions exhibit more variability than the model expects. This happens quite a bit. And more variability, well, if you just take the word more and variability and you use synonyms, it becomes overdispersion. Overdispersion, to be clear, people say, oh, I have a problem with my data. I have overdispersion. No, you don't have a problem with your data. You have a problem with your model. Your data are. Your model's wrong. It's not really a problem in and of itself. It's actually a symptom of some other problem with your model. It's often caused by having an inadequate regression model. So overdispersion often happens because you've omitted important variables from your model. It causes your observed counts to vary more around the estimated counts than they should. So if you estimate a count to be at a certain point, I draw better with my hands than on the board. If you estimate the count to be at a certain point, and there's another important variable you've left out, then that variable may say sometimes it should be up here and sometimes it should be down there, when the model thinks it should always be in here. So that extra variable is going to throw observations north and south of the predicted mean far beyond what the model thinks they should be. And that's going to lead to lots and lots of large residuals, because those residuals have accounted for the fact that the model thinks that all the data should be in here. So you'll have lots of large residuals in your plot. It also can be caused by positive correlations among the observations, such as clustered data, longitudinal data, time series data. These all have positive correlations typically, and it's basically the same thing. The positive correlations mean that groups of data have clusters that might be above or below the mean. It adds to the amount of variability in your data, just like they do in linear models. So standard models don't account for those correlations. And as a result of overdispersion, the model that you have fit to overdispersed data has variances or standard errors that are smaller than they should be. And that's a danger, because when you have underestimated the amount of variability in a problem, then your confidence intervals are too small, and your tests are too liberal. They're going to go after, and they're going to reject your null hypotheses more often than they should. So you're going to make lots of false discoveries when you ignore the overdispersion and just carry out your inferences. And as I suggested, the surest sign of overdispersion is a standardized residual plot with too many large values scattered uniformly across the plot. You have a lot of 2, 3, 4 residuals in your plot that you wouldn't really expect to have in a well-fitting model. Secondarily, you can find a large deviance over degrees of freedom, but that's not just an indication of overdispersion, because it could be large for some other reason. It's not telling you why it's large, but if you have overdispersion, it will eventually become large. But something else could also be making it large, or could instead be making it large. It usually doesn't show up in the Hosmer-Lemeshow or other Goodnessoffit tests. Does not show up. So Hosmer-Lemeshow is no good for finding that. And it can't be detected in models where you have only 2 possible outcomes. I mean, you always have either this or that. You can't have values that go beyond that ever. So you can't express overdispersion. So here's an example that woman I was telling you about who does bird counts in the cloud forests of Ecuador. This is a residual plot from a model where we fit her data to a model, and we have a residual plot where we have some residuals beyond 4, some residuals beyond 3, some residuals beyond 2. This plot is showing, and those extreme residuals are scattered somewhat throughout the plot. There's something weird going on with this observation here, but they're scattered somewhat throughout the plot. This is something that I would say represents overdispersion pretty clearly to me. So we have a third of the sample beyond plus or minus 2 when we expect 5% to be beyond plus or minus 2. And we have even any data beyond plus or minus 4, that's a big deal. Our deviance over degrees of freedom statistic is 3.73. Even the outer threshold suggests that beyond 2 is bad. So these two things are telling me that there is a problem here. The solution for overdispersion, of course, is to fix the model. I mean, the problem is the model, not the data. So if there are variables that are missing, then add them in. That's fairly obvious. If you've left some variables out, then add them in. If all the variables are already in the model, then maybe there's something else that's needed. Maybe an interaction or something is needed. If you collected your data in clusters, then maybe you need to account for the correlation among the trials somehow. And one way to do that is through a generalized linear mixed model, which is in section 7, which we added as a bonus but may not actually be able to cover. We threw extra slides in here in case we had lots of extra time, but we never have lots of extra time. And if no cause can be identified, then use a probability model that has a separate parameter for that extra dispersion. That is, change your model out of the binomial or out of the Poisson and create a new model that allows there to be more dispersion, that accepts that dispersion, and then filters that extra dispersion into the estimates of variance and standard error for the parameters so that properly adjusted inferences can be done. So in that case, you can use a negative binomial or quasi-Poisson for the Poisson regression, or a beta binomial or quasi-binomial for a logistic regression. The negative binomial model, in particular, is an alternative to the Poisson where it adds an extra parameter in to the variance. Instead of just having the variance be equal to the mean, it's equal to the mean plus some amount of the mean squared, where that amount is an unknown extra parameter that you estimate through the likelihood. So now you're going to estimate an extra parameter, and if theta equals 0, then that second term isn't there and it's just the Poisson. But if theta is much bigger than 0, then that suggests that you had overdispersion that needed to be corrected. The parameters are estimated by maximum likelihood, and the usual inference tools apply. I had to squeeze the font down on this. I apologize if it's unreadable, but if you buy a microscope, it looks fine. So the negative binomial is fit in the glm.nb function from the package mass, which Chris introduced to you earlier on, and it has kind of the same syntax as GLM, except it automatically assumes you're fitting a Poisson type model to counts. It automatically assumes, in fact, that you're fitting a negative binomial, so you don't need to list a family. It already knows the family you're choosing. You mainly just have to list the formula and where the data are coming from. And it gives you information very much like the information that we've seen before. In this case, the explanatory variable loc stands for location. There were 6 different locations in forests, in a fragment of a forest, in pastures, or along the edge of a forest. And then, ignoring this, the negative binomial parameter, so that theta, is estimated to be 33.38. And elsewhere, I was able to extract that it's shown in the program that the standard error on that 33.4 is 14.9. So just eyeballing it with an approximate eyeball wall says that seems like it might be a large parameter, and it is adjusting for overdispersion in my model. Also, my deviance over degrees of freedom is now much more well behaved. It's well within the threshold, so there doesn't seem to be as much of a problem. The likelihood ratio test for quality of the means at the 6 locations gives a tiny p-value. So the 6 locations clearly don't have the same mean, but the p-value is larger than it was before in the Poisson. I'm not showing you some of this, but I'm telling you what the results turn out to be. So it has used that extra variance and made the test statistic relatively less extreme. It's made the p-value larger than it used to be, but it's still tiny because those locations don't all have the same means. And the confidence intervals, also not shown, are much wider than in the Poisson fit, which makes them a little bit more appropriate because they're accounting for that extra variability. Okay, where are we?
Got about 15 minutes.
15 minutes. Okay. Well, I'll stop here for a moment and ask if there are any questions, and then I'll launch into a little bit of bonus coverage for you on correlated data. Do any of you teach? No, I mean teach in front of a class. In the future. Okay. Just curious.
I have one question.
Hmm?
You said it was a question. I wonder whether greenhouses could be considered to be blocks. Keep talking about the greenhouses. Are they blocks?
I didn't talk about the greenhouses other than when I was talking about that example. I would have to go back to the actual structure of the experiment, but I think I don't remember exactly how we ran it. I think it was essentially as a completely randomized design, but I don't remember exactly. Yeah, I'd have to go back to the structure of the experiment. Of course, it couldn't be a randomized complete block design because we don't have equal numbers of replicants. Okay, let's jump into a few minutes of bonus coverage here on correlated data. So all the models that we've talked about so far make a critical assumption that the data to which they were fit consist of independent observations. We didn't really talk about that, but it's an assumption basically of all models, all standard models that are fit to data. We assume that the observations are independent of one another. But in reality, data are often collected in groups. They might be collected in clusters. So, in fact, in a given, the field goal kicking is full of all kinds of this kind of stuff because we have a game that could be thought of as a cluster. And an individual game might be played in conditions that might simultaneously increase or decrease the probability of all kicks taken in that game. Oh, look, it's snowing in Green Bay. Good luck. You know, or you know, you've got a 100-mile-an-hour wind in Denver, and you could kick it from goal line to goal line. So, you know, conditions could be favorable or unfavorable for a given day. Also, kickers might vary in skill. So, multiple kicks by one kicker in the data set might be thought of as being clustered together. They belong to a group. Focus groups in marketing studies often consist of groups of individuals, and the dynamic within the group might change how they feel about certain products and certain questions. Patients within a given hospital in a research study, if you go to different hospitals, they might just generically have different results in different hospitals because some hospitals are better or worse. We hope that's not the case, but we know that it is. We know that there are hospitals that deal with more difficult problems than others, and so there are going to be hospitals that just have better outcomes than others. It might also be because of multiple measurements on the same subject. So, like in a clinical trial, you might have repeated measures, which are follow-ups on the same patient over time, or plant growth, follow-up measurements on the plant over time. So these things tend to be correlated with one another. Measurements from the same cluster or unit are usually more similar to one another than observations made on different clusters or units. So that makes them correlated because they're more similar to one another. That is, if an observation from within a group is above average, then the odds are higher that other observations within that group are also above average. Bingo, that's correlation. So performing a statistical analysis on correlated data as if they're independent is not recommended. That's one of the big things that you can do to mess up an analysis, is take correlated data and analyze them like they're independent. And in particular, when they're positively correlated, you end up with some of the same results as you get from over-dispersion. When you have a positive correlation, which is usually how correlated data work, usually when you have groups of data, they act more similarly rather than they repel one another. It can happen that there's competition, and so you tend to get quite different results deliberately in groups. But most often it's a positive correlation that brings the results together. And in that case, you have inflated type 1 error rate, and your confidence intervals are too narrow. Two basic approaches to the analysis of correlated group data are, number one, to change the structure of the model so that it correctly reflects the grouping structure of the data. In other words, have groups be a variable in your model somehow. Identify which observations belong to which groups and have groups be a part of your model. That just makes sense. And when you do that, that becomes something called a generalized linear mixed model. It's more flexible than the other approach, but it's more complicated and it can run into some difficulties that the other approach can't. And that's what the focus of this particular section is about. The other approach is to fit models assuming independence and deal with the consequences through some math and patch up the problems later. And that's the approach taken by another thing called generalized estimating equations. There are a couple of slides at the end of this section on that. I won't even get near them because we won't get that far along. So consider a population that has a lot of different groups, and those groups might be clusters or they might be subjects in a repeated measures study. The different groups often have inherently different response potential. So if you were to sample schools and sample individual children from schools, I'm sure it's easy to believe that some schools might naturally have children who do better and other schools have children who do worse than average. So those children are going to be correlated with one another. They have better response potential. Hospitals, kickers, individuals with different genetics have different response potential. So when you add the group variable in, you add the opportunity to model that response potential. But you also create some problems. And the problems are that you're not actually interested in the individual groups. I'm not trying to say, for example, which person has better genetics than which other person. I just want to account for that excess variability in my model so that I can do correct inferences. So I don't want to bring the people in, I don't want to bring the groups in a way that treats them as a part of the main analysis. I want to bring them in a way that allows me to adjust the variances in the analysis. The way we do that is by bringing them in as something called a random effects factor. So the groups are there mainly to represent other things. I didn't sample these schools because they're the only schools. I sampled these schools because they represent schools. If I sampled them because they're the only schools, I need to do a different kind of analysis. These aren't the only people I care about. These people represent a population of people. These aren't the only kickers. They represent a population of kickers, perhaps future kickers. So by bringing in random effects factors, I'm treating the levels as randomly sampled. Therefore, the effect that any one of these levels brings in is unknown to me. When I sample a new school blindly, I don't know whether it's going to be a good school or a bad school. When I get a new kicker, I don't know whether it's a good kicker or a bad kicker. Once I've gathered data, I might know, but I don't know that at the time that I sample them. So they add variability to the responses, and that's what I want. Compare that to fixed effects factors. Fixed effects factors are things like regression variables, treatment factors, covariates, and such. And those levels have systematic effects on the means, and I can always count on them. They're not randomly sampled from some population, or if they are, the numerical values give me back consistent results. So if I can possibly sample the same level again and get back the same mean result. I wouldn't do that necessarily with random groups. In order to do the analysis with random effects, we have to assume that they follow some known distribution with known parameters. And typically we'll assume that they follow a normal distribution with a mean 0 and an unknown variance. So we'll assume that the distribution of the random effects, so the distribution of the kicker effects or the school effects or whatever, is normal with a mean of 0. And the mean of 0 is because we're going to have the means accounted for in some other part of the model. What I'm really doing is asking how much above average or below average is this unit going to be. So the average is taken care of elsewhere. I just need to know, is it going to be a plus or a minus, and how much is that unit going to be? And we have an unknown variance, which adds a new parameter into the model that we need to estimate. The unknown variance is called a variance component for the random effects factor. So the variance component for schools, or the variance component for kickers. And it measures how variable members of that population are. Usually, that is a nuisance parameter in the sense that we're not trying to learn about the variability of schools or kickers. We're trying to learn about other factors, and it's just in the way. Sometimes it is important, but most times it's not. It's just a thing we have to account for. Random effects arise from grouping used for convenience. So, for example, if you want to sample 1,000 children, it's a lot easier to go to 10 schools and sample 100 each than it is to go to 1,000 schools and sample 1 each. Contemplate that for just a moment. So here's the example that we've got to demonstrate something about, about random effects. This was an example that actually my wife, who's in my department with me, worked on with some people in our biomedical physiology and kinesiology department. They studied, this was falls with head impact among seniors. They studied video footage of 227 falls among 133 residents at 2 long-term care facilities, so homes that house seniors for long-term care. They've moved there permanently, for example, in British Columbia. We're considering a reduced version of the data set that consists of the 215 falls with recorded values for all of the following variables. We have the resident, so it's just a numerical identification code for a resident whose fall was recorded. We have whether the initial direction of the fall was backward, down, forward, or sideways. And we have the variable head, which is just a binary impact indicating whether or not their head contacted the floor. So, you know, these facilities are trying to keep the residents safe, but seniors are subject to falls. It's one of the main problems with seniors is falls, and many of you may know somebody who is a senior who has experienced a fall and had some consequences from it. So they're looking at how falls occur, and then from that maybe learning something about how to possibly address the potential of head impact. So we'll ask the simple question of whether the initial direction influences the head impact. So here's a few lines of the data. We have the resident. So we have here, actually we have only 5 residents, because you might notice resident number 9 fell twice, at least in this little glimpse of the data. One time falling backwards, the other time falling down. Only one of these 6 observations involved a head impact. And this is the fall frequency. So for example, this is sad right there. Individual number 40, just in the time that they were observing, had 13 falls. This is somebody who has chronic falling problems, balance problems or strength problems or something. Here's observation number 9. They actually had 3 falls. We saw 2 of them in our top 6. And maybe the underlying mechanism causes a given resident to impact the floor in the same way each time and makes certain residents more likely to have head impacts than others. So, for example, if there were 13 head impacts in this study and they were all because of that one resident, we'd like to know that and not think that 13 different residents had head impact. That would be important to be able to understand. So for this reason, we consider resident to be a random effects factor in the analysis. I'm going to skip that and move straight on to how you handle random effects factors. So consider a simple problem where we have T groups and A responses per group. And we'll treat it as a count response, so we're doing Poisson regression, but we could do logistic regression just by replacing the log with a logit, because all the stuff that happens is over on this side. Okay, so the mean of the response for the kth response in group I is mu ik, and in a random effects model, we have the most simple form of random effects model would be to have a mean which says that everybody has the same average, but that some individuals deviate in random ways from that average. And beta 0 is the value of the linear predictor, the log mean in an average group. And then this variable here is the random effect of group I, and we assume that this collection were sampled from a normal distribution with mean of 0 and sigma squared I. So we're assuming that there is an overall mean, beta 0, and then around this overall mean, individual groups are sampled out with different effects. That is a random effects generalized linear model because we don't have any fixed effects in it. If I want to do a mixed model, then I can add fixed effects. So suppose each one of these responses has attached to it an explanatory variable. So for group I, response k within group I have an explanatory variable x. Then the log mean might change linearly with x. And a fixed effects model, which we've seen before, would just fit the log mean as a function of beta 0 plus beta 1x. And now we can augment that with a random effects variable, where these are again assumed to be a random sample from a normal distribution with a mean of 0 and a variance of sigma squared beta. What does this do? It helps if you rearrange the model a little bit. I like to write the model like this. So what we have then is that since there's no x attached to this, we have an intercept that varies randomly and a slope that's the same for all individuals. In other words, we have a picture that looks like this, where there's x and there's log mu, and we have a picture that looks kind of like that. Different individuals have different intercepts, but everybody has the same slope. And these things here vary according to a normal distribution. So there's going to be more, I didn't draw it that way, but there's going to be more of them in the middle and fewer of them on the edges. We can allow the slope to change too by adding a second random effect into the model. And when I do that, the way I like to write it out is in this manner. So now I see that the intercept has a random effect on it, and the slope has a random effect on it. So now I have something like that. Okay? I'm essentially out of time, so all I've been able to do is tell you about random effects and about how to squeeze them into models. The rest of this tells you a little bit about how to fit them, examples of different ways to put the formula together, the actual example we used, the interpretation of the results, how to do inference, and an example of the inference. And I apologize that we don't have time to do that, but we weren't sure whether we would anyway. We just thought we'd throw that in there as bonus coverage and do as much of it as we could. So instead, I'm going to jump all the way now to the end and talk about the objectives, and I'll tell you the objectives of the talk here at the end of the talk. Review the objectives of the talk. So the goals of this course or to apply appropriate methods to analyze data in a contingency table, to state, interpret, and fit logistic multinomial proportional odds and Poisson regression models, to use appropriate variable selection methods to evaluate the fit of those models, to identify and solve over-dispersion problems, and be comfortable with using R to analyze categorical data. And those objectives are relevant because the evaluation forms that you have ask whether we've achieved these objectives. And so that is a summary of the things that you can judge by. Finally, I'll point out a couple more things. First of all, I'll just remind you, there it is one more time. The stuff from today is there, including all of the programs that we have either used or referenced are all on that website. And in the back here is a list. If you remember something but don't remember where it was, there's a little bit of an index. And all of these programs, as I said, once again, are on the website that Chris put together. And now coming in at 4:57, I think we're done. And thank you all for coming, and I hope you have a good rest of your JSM.